Good morning, class. It is day 25 of Coronachem, May the 8th, 2020. These are your mock test answers. I gave you 4 questions to try out yesterday. So the first one was 2014 C, and it asks you in that question to indicate whether the following balanced equations involve oxidation reduction. If they do, identify the elements that undergo changes in oxidation number. So I picked C. C is in fact the redox equation, and you'll see why. You have sulfur dioxide turning into sulfate. We broke down the oxidation state of sulfur because that's the one that is changing. The oxygen is always at -2 for the most part in most reactions, with a few exceptions. So because it's normally at -2 and there's 2 oxygens, you should expect to have a -4 charge on the sulfur dioxide, but it has no charge. So that means something else in that molecule is +4, and that has to be the sulfur. So the sulfur in this molecule is at +4. When you go to sulfate, you have 4 oxygen atoms, each with a -2, so it should be -8, but in fact the whole molecule is at -2, which means the sulfur has to be at +6. So in this reaction, the sulfur goes from an oxidation state of +4 to +6, so it's losing 2 electrons. So loss of electrons, that's an oxidation. So the sulfur dioxide to sulfate is an oxidation. Then we look at the nitrate to nitrogen monoxide. Nitrate has 3 oxygens, and that gives you a -6 charge overall, but overall the molecule has only a -1 charge, which means something has to be +5, and that's got to be the nitrogen. So the nitrogen goes from +5 here to +2 in the nitrogen monoxide. Notice that oxygen is -2, but the whole molecule is neutral overall, so that means something else has to be +2. So from +5 to +2 means there's been the addition of 3 electrons. So this one is gaining electrons, which is a reduction. The next question is 2020 C. It's a redox. The little table here is really too small. Okay, 2020 C, it says dichromate reacts with methanol to give you methanoic acid plus chromic in acidic solution. So let's do that. So dichromate reacts with methanol to yield chromic and methanoic acid. So well, the first thing is to determine the half reactions. The dichromate turning into chromic. Let's balance that one first. So dichromate turning into chromic. There's 2 chromium atoms here. There's only 1 on this side, so I'm going to put 2 to balance that out. There's 7 oxygens on the left, so we have to put 7 waters on the right to balance out the oxygens, which creates an imbalance of 14 hydrogens. And now we can balance the charges. So we have a +12 on this side and a +6 on that side. So if we had 6 electrons, we bring them both down to +6, and that's balanced. Then we move to the second part of the equation, the second half reaction. Methanol becoming methanoic acid. 1 carbon, 1 carbon, 1 oxygen, 2 oxygens. So we're going to add 1 water molecule to balance. Then you have 4 hydrogens plus 2 hydrogens. It's 6 hydrogens versus 2. So we're going to add 4 hydrogens on this side to balance it out. And then we're going to balance the charges. That's going to take 4 electrons to balance to the same charge on both sides. Because there's no charge on this side, there's a +4 on that side. So by adding 4 electrons, we balance it. Now, let's multiply both these half reactions in such a manner that they both have the same number of electrons. If we multiply this one by 2, you'll have 12 electrons. And if we multiply this one by 3, we'll also have 12 electrons. The key to making sure you have done it correctly is to make sure that the electrons appear on opposite sides. So something is using electrons and something is giving up electrons. You can't have them both using electrons or both giving up electrons. Otherwise you have 2 reductions or 2 oxidations. So now we're going to add them together. Well, first we'll multiply everything out. So we're going to have 2 dichromates times 2 gives you, yeah, right. Plus 2 times the 14 gives you 28 hydrogens. Plus 12 electrons, plus 3 times the methanol, plus 3 waters. And then we're going to have on the right side of the equation 4 chromiums, plus 14 waters, plus 3 methanoic acids, plus 12 hydrogens, plus 12 electrons. The electrons will cancel. The hydrogens will also partially cancel, so you're going to have now 16 on the left, sorry. The waters also partially cancel, so that you have 11 waters on the right. And now we can write the final equation, but remember that they're asking us, okay, it's in acidic solution, so we don't have to do anything after that. So we write the net equation now. 2 dichromates plus 3 methanols, it's also going to be aqueous, plus 16 hydrogens, aqueous, yields 4 chromics, aqueous, plus 3 methanoic acids, aqueous, plus 11 water, which would be liquid because it's part of the solid. And there's your balanced redox reaction. That was 2020C. The next thing I assigned for the mock test was E, 2020E. Let's do that one as well. So Monday's going to be your real test, guys, so take some time to study this weekend. 2020E is peroxide reacting with chlorine dioxide to give you chlorite plus oxygen. So peroxide plus chlorine dioxide reacting to give you, I already forgot, chlorite and oxygen. Let's double check I got everything right in the right symbols. Chlorite, O2 gas. Oh, got a minus sign. Chlorine dioxide. Yeah. Okay. So that's the redox equation we have to solve. So we have to start off with peroxide turning into oxygen, and we have the same number of oxygens on both sides, so we don't have to worry about that, but we're going to add 2 H pluses on this side. Now we can balance the charges. There's a 2 plus charges here, nothing on the left, so we're going to put 2 electrons, and that's going to be balanced for that half reaction. Then we have the chlorine dioxide turning into chlorite. Same chemicals, the only difference is there are electrons, or more electrons on one side. So we're going to put this in, put one electron to balance that one negative charge, and that's it. Oh boy, that's an easy one, I think. Multiply that by 2 to get the same number of electrons and add the results. We're going to get H2O2 plus 2ClO2 plus 2 electrons gives you O2 plus 2H2 plus 2 electrons plus 2 chlorides. Alright? And that allows you to cancel the electrons. And there's nothing else to cancel, but remember we're being asked to do this one under basic conditions, so we're going to add 2 hydroxides to the right side. Of course, if we do it to the right side, we have to do it to the left side, but the aim here is to turn this into water and then have the thing balanced under basic conditions. Let's write the net equation now. We have 2 waters on this side, no waters on the left, so we can just put everything in its final phase. So the peroxide is aqueous, the chlorine dioxide is aqueous. It's going to be the same as in the book. Yeah. Then you have 2 hydroxide, aqueous, plus O2 gas, plus 2H2O liquid, plus 2 chlorides, aqueous. And you're done. That's your final answer for 2020C. The next question I asked you to do was 2024. In 2024, you're asked to, it says a voltaic cell similar to that shown in figure 20.5 is constructed. One electrode compartment consists of an aluminum strip placed in a solution of aluminum nitrate, and the other has a nickel strip placed in a solution of nickel sulfate. The overall reaction is 2 aluminums plus 3 nickel plus 2 turns into 2 aluminum plus 3 nickel solid. What is being oxidized? What is being reduced? B, write the half reactions that occur in the 2 electrode compartments. C, which electrode is the anode and which is the cathode. D, indicate the signs of the electrodes. And do electrons flow from the aluminum electrode to the nickel electrode or from the nickel to the aluminum? In which direction do the cations and anions migrate through the solution? Assume the aluminum is not coated with its oxide. Okay, let me just check one thing here. I'll start by drawing the electrode. Okay. There. You always draw the anode on the left. So you draw 2 beakers. You draw a salt bridge so that the charges can equalize. You draw your metallic strips so that the electricity can make, so the solutions can make contact with the metal. So this is the anode side, this is the cathode side. So on the anode side you have the oxidation reaction, and on the cathode side you have the reduction. This is an aluminum strip. There are, well, obviously there's some solution in there. So you have aluminum nitrate in solution. So there are cations of aluminum. There's also nitrate anions floating around. And when the aluminum leaves the surface, it also leaves behind 3 electrons. So the electrons are leaving the anode and they're going towards the cathode. On the cathode side, which is where the reduction is taking place, nickel ions are floating in solution, and there's also sulfate anions. So the nickel anions are drawn to the presence of electrons because there's a negative charge buildup in that plate, and so the nickel cations go there and they deposit onto that surface. So the nickel is being reduced onto the surface. What's happening at the anode is the aluminum is coming off the surface, so the anode is getting lighter. It's losing weight, whereas the cathode is getting heavier. Now let's answer the questions. Also, as the nickel ion concentration decreases in this solution, these sulfate anions will tend to move into the bridge to go to the other side. And likewise, as the aluminum ion concentration increases in solution, you're going to need more negatively charged species to counterbalance it. So you're going to have the sulfate anions trying to creep on. I don't know if they'll actually reach, but you'll have a net movement of whatever negatively charged salt you have in here. You could have, I don't know, sodium nitrate if you want. So whatever is negatively charged will tend to go this way. Whatever is positively charged will tend to go that way, because it's trying to equalize the charges that are, the positive charges that are building up on this side. And here the positive charges are going down, so you're going to get a net movement of negative charges that way. So let's answer the questions, the specific questions now that we've drawn the diagram. 220, what is being oxidized, what is being reduced? That's question A right there. B, write the half reactions that occur in the 2 electrode compartments. Okay. So in the first case here, let's call this, well, it's the anode. I'll write it under the anode. So at the anode, what you have is aluminum turning into aluminum 3+ plus 3 electrons. And on the cathode compartment, you have nickel being reduced to form elemental nickel. Part C. Which electrode is the anode and which is the cathode? I guess that's the answer here. That's C. D. Indicate the signs of the electrodes. Okay, this is a tricky part because it also bothers me. For whatever reason, they put the sign conventions backwards. They put the plus sign on the cathode and the negative sign on the anode. Let me double check that, because one answer that I'm not sure of because of the messed up conventions. And 23, when a teacher is not sure, that's the bad thing. So let's make extra sure, because it's giving you, my spider sense is tingling. 23, okay. If yes is negative for the previous one. Sorry for all the movement. It's because I have one little table to do everything on. D. Cathode is negative and the anode is positive. Anode is positive. I had it backwards, just as I thought. Okay, there we go. So what's going on is electrons are leaving here. So yeah, stands to the reason that the call that positive. And then electrons are appearing here, so there's a surplus of negative charge here. That's what's attracting. What attracts cations to the cathode? Well, it's the fact that the cathode has electrons present. That's what attracts those positive charges of the cations. Okay. D. That's done here. Okay, and then E, it's asking (2024) E. Do electrons flow from the aluminum electrode to the nickel electrode or from the nickel to the aluminum? They go from the aluminum to the nickel. And is there an F? I think I may have forgotten to answer F, yeah. In which direction do the cations and anions migrate through the solution? Assume the aluminum is not coated with its oxide. In here, on the anode side, cations move into solution from the electrode, and on the cathode side, cations move towards the electrode. Okay, that's all the parts of that question have been answered now. Okay, the next question is, I really need a second table. The next question is 2034 A, B, C, no. Is it 34? Because I remember last minute decision, yes. 2034 A, B, C, D. Using the data in Appendix E, calculate the standard EMF for each of the following reactions. So, okay, 2034 it is. I would have just shown you my notebook to do this, but it was just too messy for you to get anything out of it. I'm going to have to rewrite this notebook. So that's why I did it on the board. But I've noticed that the upload rates up here in the country are frightfully slow. It literally takes an hour to upload a 1 hour long, a half-hour video. Actually, what am I saying? It took several hours to upload a half-hour video, so I realized that I can't be uploading those videos the same way as I do in the city. Anyway, we'll do what we can. So 2434A, H2 gas is turning into 2H plus 2 electrons. So that's 0 volts if you look it up in the standard reduction protection. And the other one is fluorine gas plus 2 electrons turns into, yeah, I guess it is right, into two fluorides, aqueous, and that's negative, positive 2.87 volts. So when you add those two half reactions together, E naught cell will become 2.87 volts. For B, we have copper solid turning into cupric ions plus 2 electrons. That has a half reaction potential of negative 0.337 volts. And barium plus 2 electrons gives you barium solid, and that has a negative 2.90 potential. So the reaction as written has a negative cell potential, which means it tends to run the other way. To run the reaction the way it's written in the book would require an input of energy. You would get negative 3.237. So the reaction wouldn't go that way, it would go the other way. So copper solid, barium 2+. Yeah, now the way it's written would require an input of energy. So 2434C, iron disproportionating. Okay, so we have iron atoms. My answer in this question is not clear. So we have 3 Fe2+ aqueous going in one instance to become solid elemental iron, so that will require the addition of 2 electrons. And let's break down the 2 reactions first, and then we'll look up the potentials. And in the second half of the reaction, we also have 3 Fe2+, but what's happening in that case is it's becoming Fe3+. So it's losing an electron. Now let's look up the cell potentials for both of those. So Fe being reduced will be negative 0.440 volts, and iron being further oxidized from 2 to 3 will be negative 0.771, because we have it written as reduction potential in the textbook. Yeah, so it's negative 0.771. So if you were to set up the reaction as written, the voltage would come out to 0.44 plus 0.771, it would be negative 1.211. So this reaction is unlikely to happen as written, because the net reaction is 2 Fe2+. I don't know why I put a 3 here. 2 Fe2+ turning into Fe solid plus Fe3+. Okay, so the reaction as written would require the input of 1.211 volts. it's not likely to occur. Finally, the last step, just erase the top part here, 22034D. Shows you mercurous ion reacting with two cuprous ions to yield liquid mercury, or elemental mercury, plus two cupric ions. So let's separate the half reactions, and then we'll look up the individual potentials. So we have the mercurous cation turning into elemental mercury, and we have cuprous turning into cupric, two in that case. This is going to require that two electrons are here, and on this one, two electrons have to be added. Okay, so those two reactions add up to that. Now let's look up the potentials for both of those. Remember, if you multiply a reaction, it doesn't affect the voltage, right? You just get twice the same reaction. But the voltage stays the same even though you multiply it. It's like saying you can have twice as much water coming over the waterfall, but the waterfall is still the same height. The water falling over the fall still has the same amount of energy. So multiplying reactions does not change the voltage. Just remember that when you do calculations. So the potential for the mercurous ion turning into elemental mercury, let me see, Hg, where are you? Here it is. Okay. Hg2 plus 2 electrons gives you 2 Hg, 0.789 plus 0.789. Okay, and the other one is cuprous turning into cupric. It's written backwards from what you see in the book. So the voltage is reversed, is negative 0.153. So the total voltage will be those two added together. So the cell voltage is 0.789 minus 0.153, and you get 0.636 volts. Okay, there's your cell voltage, your Anions cell for that. And that wraps it up for today. On Monday, I'll give you the real test. Okay? So study, and we'll see you Monday.